Okay, welcome everybody. It's a real pleasure to have here today Ira Rothstein from Carnegie Mellon, who is in fact this year in sabbatical in Edinburgh, and Ira is a world-leading expert on effective field theories applied to many different contexts, in particular to QCD jets and also gravitational interactions. And today he's going to tell us how to understand the high energy limit of quantum field theory. Please, Ira.
Thank you. Thanks for inviting me, Carlo. I appreciate it. It's nice to be here and see familiar faces. So, I'd like to talk about the high energy limit of quantum field theory, and the usual colloquium disclaimers apply. I'll try to engage the non-experts without offending the experts, and I probably won't succeed in either. But okay, so a big chunk of this work was done, of the older work on QCD was done with Ian Stewart, and the stuff on gravity, which I'll talk about in the end, was done with my former student, who's now at UCLA, Michael Saavedra. Okay, so I don't have to tell everyone in the audience the power of field theory. And what makes field theory difficult is the infinite number of degrees of freedom, as you all know. So the richness of all the phenomena which the power of field theory is encompassed by the fact that, that it avoids the Stone-von Neumann theorem, right? So in quantum mechanics, Stone and von Neumann told us that there's only one representation of the Heisenberg algebra that's unitarily, there's only one unitarily inequivalent representation of the algebra. But the field theory avoids this problem by having infinite number of degrees of freedom. So the proof of this theorem assumes you have a finite number of degrees of freedom. So the loophole in that theorem is what makes life interesting. So, when it comes to field theory, we're interested usually in the low energy degrees of freedom. So that's obviously not always true if we're interested in quantum gravity. And I'm also going to mod out by conformal field theories. So when space-time symmetries are unbroken, the low-lying degrees of freedom are typically Goldstone modes, or possibly other modes, gapless modes, which are there for symmetry reasons, like gauge bosons or fermions. And I think it's probably true that for trivial vacuums, the ones that don't break any space-time symmetries, field theory is pretty well understood, at least in the IR. So if our underlying degrees of freedom are just Goldstones and we're in a trivial vacuum, their low energies are going to be derivatively coupled. And then if we have other modes around for symmetry reasons, say if we gauge them, even for strong coupling, even if that theory were strongly coupled, Euclidean field theory suffices at low energies in trivial backgrounds, and we have the lattice to save us. So I think it's fair to say we have a pretty good handle on those problems. There aren't too many open, vexing problems in that subcategory of field theories. But when space-time symmetries are broken, things get a lot more interesting. So we can consider the presence of classical sources or work at finite chemical potential. And this is in my opinion, the class of theories where the really interesting open conceptual problems exist. And I'll tell you what I mean by how general this statement is. So here are some examples of what I my personal bias as to what the most important conceptual problems in field theory are. Of course, these are based on my knowledge and my ignorance, so take that for what you wish. So one of them is that is more recent is non-Fermi liquids, which are field theories where there's no well-defined notion of asymptotic states. So usually it's defined as one where, say, So this is a case, of course, where space-time symmetries are broken. And it's usually defined as when the quasi-particle width is so broad that you can't even talk about the notion of a particle. But it's not a conformal field theory. So there's no S matrix, but it's not a conformal field theory. And no one really has a systematic way of calculating in these theories, despite the fact that they're ubiquitous in quantum matter and many of the interesting effects in materials that we don't understand. And then there's also flat band systems, this is a more recent topic involving graphene and so forth. These systems where there's the energy is independent of the momentum, and the potential energy just dominates, right? So we don't really know how to formulate that in a field theory. So actually, this is also an interesting case. What happens in a fluid if you try to quantize a perfect fluid? The same thing happens, and that's an open question. Whether or not that's of relevance to any phenomenology, of course, is a different story. And then the topic I'm going to talk about today, which is high energy forward scattering. And you could ask, well, why is this? Well, first of all, in what sense does this break space-time symmetries? And I'll explain that in a second. And the other question you should ask is why don't we have a handle on this through the lattice? And the answer is because it's an inherently Minkowskian scenario, right? So it poses serious challenges to any sort of numerical computations. And I didn't, of course, the other problem that is the crazy uncle in the closet is turbulence. But I didn't include that because that's not really a question where we can start asking it. It's a system where you're pumping in energy and stuff is flowing to the UV, so it's not clear how to make sense of that from the point of view of an effective field theory. Okay, so we're interested. So high energy scattering. Why is this an effective field theory? If we're interested in if I'm talking about low-lying excitations, and what does this have to do with space-time symmetry breaking? Well, because the way to think about this high energy process. So here's two incoming guys, and they're exchanging soft radiation, and they collinear radiate. And so you should really think about this as two sort of classical sources, which are breaking space-time symmetries. And we're interested in fluctuations around this non-trivial ground state, right? So in that sense, it's more like a system with a broken space-time symmetries. Okay, the difference between the forward scattering problem and the other ones I mentioned is that this has been around for many, many years. And there are countless books written on the subject, and probably some people in the audience may even have written one. I'm sure there are experts in the audience. And so the question is, why am I talking about this if this is such an old subject? So let me give you a few reasons why you might be interested in hearing what I say. So I'm going to show you how we approach this problem from a point of view of an effective field theory. And these techniques have been used in QCD for about 5 or 6 years now, maybe a little bit more. Hasn't really been applied to gravity as much, which is what I'm going to talk about towards the end of my talk today. But I sort of think of it like how we revisited S-matrix theory when the amplitudes program started. So we have a new technology. Let's apply it, and let's see if we can learn anything new. And then I'll tell you whether or not, we're still trying to make progress. As I said, also, forward scattering gravity is not as well explored. None of those books discuss gravity. So there are multiple puzzles when it comes to forward scattering gravity that were, I should say that the ACV wrote a set of papers where they sort of introduced this question of what happens with super Planckian scattering. So I'll talk about what happens at the end of my talk in gravity when when S becomes much larger than m Planck, when this total center of mass energy is much larger than m Planck. And finally, because gravitational wave astronomy has gathered a lot of attention from the high energy community, who've been applying their tools to this problem of calculating precision gravitational wave templates. And now the amplitudes community has made significant progress in these calculations as applied to binary inspirals going to very high orders. And so that question is, why is the forward limit interesting? And I'm going to show you is that it has the ability to do resummations. Whether or not you're resumming things you're interested in, or whether or not the resummation is systematic, of course, is a different question. Okay, so why is forward scattering harder than wide angle scattering? So and I wrote this slide keeping in mind that there might be people in the condensed matter community here who aren't familiar with some of the notation. So these are the Mandelstam variables. So P1, P2 are incoming, P3 and P4 are outgoing. And 2-to-2 scattering amplitude can be written by Lorentz invariance as some analytic function of S and T. Those are the two independent ones. There's a constraint U I haven't written down as P1 minus P4 squared. So the amplitude can be written as a function of S and T. Now in hard scattering, all these Mandelstam invariants are of the same order. Okay, so you don't have any large hierarchies of scales, and hierarchies of scales are what make field theories harder. So it's not that this is easy, but it's relatively easy compared to the forward scattering case, which I'll get to in a second, sorry. So this, I claim, is an inherently, these short distance phenomena are inherently Euclidean in some sense. But whereas forward scattering is Minkowskian, because in forward scattering we have to have, even though all the energies are very high, it's still true that T can be small because of the minus sign in the metric. So you have very high energies, but T is the momentum exchange can be thought of as the momentum exchange. So glancing collision when T is small. Okay? So you can't have this hierarchy if you're Euclidean. So that's what I meant when I said that high energy scattering in this respect is a completely Minkowskian process, which is what makes it harder to study on the lattice. So what's interesting about if you start to calculate is that even for weak coupling perturbation theory, the amplitude of the expansion will break down. So even if alpha is small, of course this happens in QCD all the time, but alpha runs. And I'll explain to you in a second why this is inherently different than that. So these logs of S over T are what's known as Regge logs. However, these logs are not canonical renormalization group logs. And this is related to the statement that this is an inherently Minkowskian process. So they're a different beast than the usual logs. And if you want to resum these logs, you can't just open up a textbook to do it. Well, some of the textbooks that I showed you were, but I mean not the canonical field theory textbooks. So the Wilsonian RG, which is how we sum logs, is inherently Euclidean. Of course, that's very clear from understanding how it's applied to statistical mechanics. We have some RG flow as we lower the cutoff, but we're lowering the cutoff, we're lowering all the momenta simultaneously. So in that sense, this thing is resumming logs which are invariant mass logs. They're logs of ratios of invariant masses. And all those invariant masses are large. Sorry, not large, but the ratio of invariant masses that you're summing. You have the log of invariant ratios, that you're summing as you flow in this. And all the momenta scales, all the P's There's no hierarchy in the individual p's. Okay, but this doesn't suffice for forward scattering because in forward scattering there's no large virtualities anywhere, right? So the normal Wilsonian picture is we're thinning out degrees of freedom, right? We're coarse graining, right? But there's nothing to coarse grain. Because if you look at the loop diagram, if you were to calculate these loops, there's no large energy flowing anywhere. So there's no large S anywhere in this diagram. So there's some small soft momentum going through here, but there's no large virtualities anywhere. All the virtualities are small. So the usual program that we apply doesn't work for these so-called Regge logarithms. Okay, so if these aren't the usual Wilsonian logs, what are they? They're not large ratios of invariant masses. They're large ratios of rapidities. So here I'm working. These are light cone momenta. So one incoming guy has a large p plus, and the other incoming guy has a large p minus, and p plus p minus will give s. So what happens is, so the final answer has a log s over t, so you would say, wait a second, no, sure there's a large invariant mass in that log. So it must be running through the loop, and that's not correct. What's happening is that you get two logs, one log of the large energy of one guy, incoming guy, one log of the other guy, and they combine to a log s over t. But you shouldn't think of this as a hard log. It's actually a log in the ratio of rapidities that are combining to form this log s over t, which it has to by Lorentz invariance. So these rapidity logs show up in many observables. As I said, so in near forward scattering, they're resummed using the BFKL equation, which is a diagrammatic approach where you draw Feynman diagrams and you figure out what the leading ordering is in rapidity as you make more and more emissions. It shows up in the massive light-like pseudo-Coff form factor. What I mean by this is the gauge boson is massive, but the external lines are massless. And it also shows up, say, in transverse momentum distributions for particle production. So if you look at cases where PT is much less than Q at the LHC, then you need to sum log of PT over Q, and those guys turn out to be rapidity logs. And so there are different methods for summing all these logs, and what I'd like to show you is that there's sort of a unifying method which can do all these within the same logical structure. Okay. Seems to be skipping some. Okay. So what we would like to do is figure out how to sum these logs using an effective field theory. Okay? So we wanted to figure out how to generalize the notion of RG flow. Okay? And in order to do that, we have to understand how to build effective field theories of systems with non-trivial vacua. So we know the canonical trivial vacuum effective field theories say when we integrate out a heavy particle, like in 4-Fermi theory. So more non-trivial EFTs, which are now still under study, are where you have non-trivial vacua. So what I mean by that is you have some sort of selection rule or some classical source that's breaking your space-time symmetries. And the classic example, say, is a heavy particle that's just sitting there. So the ground state is composed of some heavy particle, and there's a conservation law, so you could actually think of it as a super selection sector. So you have it's a new Hilbert space around which you're expanding, and it is no way, it's completely disjoint from the usual trivial vacuum Hilbert space. So the classic example is a heavy quark effective theory. So now if you have some heavy quark, what you want to do is You want to eliminate the mass is taken to infinity. It's just a source. It's not playing any dynamical role. And so you scale out the mass from the field. Now derivatives on this field will all be small relative to the mass because you've removed the mass. Okay, so this is just a standard rephasing of the field so that this guy only has support over small momenta. And the field is labeled by some velocity because that determines a superselection sector. That velocity doesn't change. Okay, so a more non-trivial example. So this is sort of an old story. A newer, still old story is non-trivial vacua composed of light-like energetic sources as opposed to just static, massive ones. And the effective field theory for that is called SET, which I'll say a little bit about in a little bit. But what makes these interesting is what they're called, what I call modal effective field theories, where the fields are broken up into different modes. Okay, and I'll explain that a little bit. What modes should you break the field up into? Okay, so if you're interested in low energy theory, all you're interested in is reproducing all the non-analytic structure of the theory. And all the non-analytic structure we know comes from cuts that arise due to particle production, so they have to be physical processes. Okay, so you want to isolate the regions of so you're breaking up the field into different regions, and you want to isolate the pieces that you're interested at low energies and throw out everything else. So what pieces are you interested in? You're interested in the modes which keep everything on shell. So this goes back to just the Landau equations, or more physically, the Coleman-Norton theorem. Sorry, I misspelled Coleman. Which tells you that the relevant degrees of freedom are the ones which create physical on-shell processes. So if you have some particle coming with P, say, and this is a energetic guy, and it's emitting some soft radiation, or let's see, it could be collinear radiation. So these guys are nearly on shell. They have some small virtuality. And this whole thing, we know, is going to create a singularity when this thing goes to 0. So the kinematic configurations which this can occur are when they're either P is collinear to K or P is soft. So that's telling us we should take our field and break it up into soft pieces and collinear pieces. Sometimes if you're doing hard scattering, you want to, of course, eliminate the hard piece altogether because it's, in some sense, irrelevant to the low energy degrees of freedom. Now, what's sort of interesting, this seems really simple, but it actually gets more complicated because we don't know, when I said these are on shell and they have some 0 virtuality, they could have different virtualities and both be small in the power counting that you're interested in. So what can happen is that the soft and the collinear modes can have small k-squared, but they could scale differently. And I'm not going to go into this, but you have different effective field theories depending whether or not the collinears have larger virtualities than the soft, and that depends. For instance, if you're working at the LHC, you're going to put in some sort of angular resolution on your jets, and that's going to give you the typical collinear virtuality. And if you're going to veto, say, on soft modes, that's going to give you your typical soft virtuality. So you're going to get very complicated theories depending upon what observables you choose and what your cuts are at the LHC. Okay. Okay, so this is what I just said. And so now how do we split the field up? So we write the field to say some sum of collinear modes and a soft mode. I'm choosing one particular simple example. So we're going to slice and dice the field space up. And as in the case of the heavy particle, we want to get rid of this large energy so that all derivatives are small. So we scale out this large energy of the collinear lines. Now, the difference between this and, say, the heavy particle is that when you have a collinear emission, you can change this energy. So this is not, it's not as useful to think of this as super selection sectors. So there'll be interactions where these labels on the fields will change. Okay, now when there is a hard scattering involved, which is what happens in only 10% of the processes at the LHC, maybe less than that, something really simple happens. So the action can be written as a sum of a piece with only collinear fields and a piece with only soft fields, up to corrections which are down by the high energy. So if you're interested in in QCD phenomena, then these corrections will typically be like lambda QCD over Q, which can be tiny in most instances as long as you're looking at really wide angle scattering. As a consequence of that, the stress energy tensor can be written as a sum of the collinear piece and a soft piece. And that has a remarkable simplification because essentially it tells you that the Hilbert spaces of the soft and the collinear pieces become just a tensor product, right? And why that's so useful is because if you start taking matrix elements, then a matrix element of a complicated operator product just becomes products of individual simpler matrix elements. You have that's called factorization. So, and in this case where you have hard scattering, actually it's true more generally, you have an emergent symmetry. So these collinear, if you start off with an SUN or whatever your gauge group is for Yang-Mills theory, then there'll be an individual gauge symmetry for each sector. So you went from SUN to this enhanced symmetry for each sector. Okay, so this is, as I said, this theory was called SCT, was developed in the early 2000s. And the idea is, as I said, you have some hard scattering, you integrate out this hard mode to get a local operator, and then you just have fluctuations due to soft and collinear modes. So if you're looking, say, at a scattering amplitude, or actually this is the square of the amplitude, this is you're going to take the imaginary part of this thing, then a general scattering process will look like some hard matching coefficient, which comes from integrating out all the Wilsonian logarithms. Everything here is completely Wilsonian. And now you've got an incoming proton and an antiproton, or whatever, not an antiproton, but a proton coming in the opposite direction. And then you have some operator, and this is where the factorization pays off, because now, because the Hilbert spaces are distinct, it's a product space, then you can just write it in this way. And these things turn out to be just nothing more than the part-time distribution functions. Okay, so that's not what we're interested in. That was just an introduction to understand how to do a modal effective field theory. But forward scattering is more complicated, because when you're forward scattering, these collinear lines don't decouple like they did in the previous case, because they can talk to each other. So the way to see that is, again, using light co-momentum. So we have some collinear line. I'm going to define my expansion parameter as T over S, which is some small number. So if I have a collinear line in the n direction, it has this 1 is in the units of S. So this is very large energy. It has one very large component. The P plus is very large. The P minus is very small. And the transverse momentum is small. And then similarly, I have a guy in the opposite direction where now P plus is small. P minus is, P plus is small. P minus is large. And some transverse momentum. And what happens in this case, because these guys share the same transverse momentum because they're both along the beam pipe, you can exchange gluons, in the case of QCD, with momentum which scale like this. And the reason is because you could see that adding this momentum to this momentum and squaring it leaves it on shell, right? And that wasn't possible when you had a hard scattering. So these new modes are called Glauber modes, named after Roy Glauber, because they're related to such things in optics. So what happens is that now this factorization is ruined. And from the point of view of effective field theory, you generate an operator that looks like. So if I have just one Glauber exchange, here I'm allowing all sorts of possible soft interactions here. But if I just look at one Glauber exchange, I would generate an operator that looks like this. This ON is just a bilinear in the n fields. This ON bar is a bilinear in the ON bar fields. And this 1 over P perp squared is the fact that the Glauber propagator only has this piece, and these pieces are small. You can neglect them. So they violate factorization, and that's why we don't have a handle on 90% of the data at the LHC. Because anything where you have anytime we have forward scattering, we have factorization violation, and we can't write things in terms of PDFs, and all our intuition about what happened, how we predict things, just fails. So that's why this is such a challenge to try to understand a big chunk of the data at the LHC, which is not understood. Okay, so what one does is there's going to be an operator for each possible exchange here, and in principle there could be different numbers of gluons on top and on the bottom. So we need to write down the amplitude in terms of this infinite set of operators. So this is what essentially it looks like. So this is a jet on top, and this is the jet on bottom. And then there's this soft piece, which includes all the Glaubers. So this SNM means I've got n Glaubers coming up the top into the soft loop, and I've got m Glaubers coming out on the bottom, out of the soft loop, talking to the bottom. And the color indices here are a bit nasty. I'm going to just suppress them for the moment. And so you can see that the amplitude is some convolution in transverse momentum over this complicated object. And so this is where the problem starts to spiral out of calculational control. Okay, now if you start calculating these diagrams, as I'll show you in a little bit, you'll see that you generate logarithms of s over t. These are these Regge logs I had mentioned previously. And we have to figure out how we're going to sum them. As I said, these are not logs of invariant mass. They're logs of rapidity ratios. And the underlying reason these logs show up is because if we look at how we decompose the field, so here I am in the space of k plus and k minus. So the collinear modes sit here at large k minus, small k plus. The anti-collinear modes, large k plus, small k minus. And the soft modes sit in somewhere around here. And the important thing to understand is that they all have the same invariant mass. So the question is, how do you distinguish them? Right? So is this guy soft? Or if I start moving it over here, is it collinear? If I move it up here, is it n-bar collinear? So we have to have some way to distinguish these modes, much like in a Wilsonian RG, we have to have some way to distinguish hard modes from soft modes. We have a cutoff in invariant mass, or in lambda in Euclidean. So we have to introduce some notion of a rapidity factorization scale. Right? So this would be the analog of what we call the factorization scale in hard scattering, which is usually we do dimensional regularization. It naturally introduces the scale mu, which separates out the hard and the soft. We need something else to separate the soft from the collinears. Okay, so to understand this, let's go back and talk what kind of integrals are the cause of these logs. So these logs come from rapidity divergences. So they come from integrals over dk plus over k or k minus, either way, which obviously diverge and are not regulated by dimensional regularization. Right? So the mu scale can't be the relevant scale here to factorize. Right? And if we break up the integral into small k plus, we'll call this the soft piece, and we'll call this the collinear piece, and we'll call lambda a rapidity factorization scale. Now, of course, we don't want to do this because we're going to butcher gauge symmetry, which is the usual problem when introducing a cutoff. So we have to put in some other regulator, and there are different ways of doing that. And the way we did it was by introducing a regulator which explicitly breaks boost invariance and a scale nu. So we should expect our integrals to diverge when eta goes to 0. And we should also expect that this butchering of boost invariance should not be a problem once we add up all the sectors and all the boost invariance breaking will disappear. So let me give you a simple example so you can get a better sort of feeling for what's going on. So this is the triangle diagram for the Sudakov form factor in the light-like case, and I've put in a mass for the gauge boson. So this integral, if you do the integral by contours for you'll see that you're going to run into a dk plus I take it back. So this integral is fine. This is the full theory integral. But now when we break it up into regions, there's going to be, we have collinear exchanges and we have soft exchanges. And this is what the effective field theory to do, and it exactly reproduces the method of regions or asymptotic expansion of integrands. So we asymptotically expand, essentially the EFT does this at the level of the action, and it asymptotically expands so that you're only, here's the piece where you're getting the contribution from the soft region, so I'm dropping the k-squareds here, right? And here's a piece where, here's the collinear piece where I have to keep the k-squared. So this integral, you can see, this is k plus and k minus, will not be regulated by dimensional regularization, and neither will this one. So putting in that eta regulator, what happens is you can calculate it, and you get this eta pole. So this is the rapidity divergence. And we get this nu here, and these new logarithms, which are going to be, we're going to build up the rapidity logarithms. And if you add up the collinear and the soft pieces, you'll reproduce the exact result here. All the 1 over etas will cancel. So notice there's a minus 1 over 4 pi squared eta. There's 1 over 8 pi squared because there's also the anti-collinear region. So when I add this and this, all the eta divergences will cancel. So if you, as I said, if you add them up, it looks well behaved, and you just reproduce the full theory result. The other thing we notice is that, so if you look, as I said before, there's no S anywhere. So the collinear piece only knows about P1 plus. The anti-collinear piece will know about the other momentum. And it's only when you combine them that you're going to get a log of S over T. Or in this case, the rho of T is M. So you get a log of Q over M. So that's the analog of the rapidity log. OK? So to sum the logs, what we do is we define a rapidity anomalous dimension. Oops. In the usual way. And then we run, just like in the usual case, we have a choice. We can either run the soft piece up to the hard scale or the hard piece down to the soft scale in invariant mass. We can run the collinear piece in rapidity down to the rapidity of the soft, or we can run the rapidity of the soft up to the collinear, either way. And then if you do that, then the RG equation is trivial, and the solution just resums those rapidity logarithms. So that's the sort of the canonical example. OK, so in forward scattering, I should say there, in this case, in the Sudakov form factor, there's also mu dependence here. So there's also, there's, in addition to rapidity logs, there are Wilsonian logs as well. But in the forward scattering, there's only rapidity logs. And so what we're going to do is try to resum the logs, say, run the soft piece in rapidity from the low rapidity scale to the high rapidity scale. So from square root of T to square root of S. So each of these operators has its own rapidity anomalous dimension. And so we can start calculating these anomalous dimensions. And it turns out, I don't have time to go into this here, but this matrix of anomalous dimensions has a lot of structure. So if you impose crossing symmetry and unitarity, it turns out that many of these anomalous dimensions are related to each other. And we're just now trying to unravel the structure of the anomalous dimension matrix. OK, so let's do some examples. So if we just look at S11 corresponding to one Glauber exchange and calculate its anomalous dimension, then we get this IR divergent quantity, which is not surprising because we're not looking at an IR-safe object. But for one Glauber exchange, we can calculate the amplitude and resum all the logs, and it looks something like this. And this is called the gluon-Regge trajectory in the old-fashioned way of saying things. The gluon-Regge trajectory is nothing more than the anomalous dimension of the one Glauber exchange. So this is sort of a different way to think about it. If we go to two-Glauber exchange, then things have got more complicated because the RG equation is a convolution in transverse momentum. So for instance, we could look at the running. In this case, I'm looking at the running of the collinear guy, of the collinear piece. Obeys this rapidity anomalous dimensions. So there's two pieces. There's this delta function piece. This is known as the Regge pole. And then there's this what's known as the BFKL kernel, and that's called the Regge cut for reasons related to Regge's theory of dispersion relations and scattering, angular momentum space. So this is called the BFKL equation, and if you wanted to, you could go three gluons and write down the RG equation for that. There's no name for that. And of course, there's also, what I haven't really talked about as fact is that there are, so when you have two gluons, you have to break it up into color irreps. And the BFKL equation is usually one for the octet 8, the antisymmetric octet exchange. But there's also the pomeron, that's the singlet. And then there's whatever tensor representations you can build up. As you add more and more Glaubers, it just spirals out of control. So this is one of the things that makes QCD so much harder than gravity in some respects is this color problem, right? That in gravity, it doesn't present, gravity presents its own challenges. Now the problem is that even if the coupling, remember, so these logs are not RG logs. So the coupling you can choose, the coupling will always be evaluated at T. So say you chose T to be above the QCD scale, so the theory is still weakly coupled, right? As S over T goes to infinity, so if you take S to infinity holding T fixed, alpha remains the same, still small, but the theory will still break down nonetheless, right? Because the logs are going to be so big that resumming leading logs won't be enough, resumming next leading logs won't be enough, whatever. So it's telling you that you've got the wrong degrees of freedom. So as S over T is getting large, you're starting to probe a new sector of the theory. So the way that I think it's thought about is that you're basically, you're expanding around the wrong vacuum, right? You should be expanding. What happens is you have you have soft gluons that are proliferating, and you should be expanding around some classical field configurations. And this is in this context, this is how I understand what's known as the color glass condensate, which people believe is the correct or the correct representation of the theory. Okay, so now let's consider gravity. So we want to write down an effective field theory of gravity.
Maybe a question?
Yeah, sure. Yeah.
Going to gravity.
Yeah.
So what is the difference with QED? So you never mentioned.
So
this.
QED is a lot simpler. So for instance, because for instance, the photon has no Regge trajectory because it's completely non-abelian. So also if you're talking about massless QED or
no, with the
massive QED, but with
massive electrons.
Say T much larger than ME and S much larger than ME. Yeah, so you don't run into the problems with these rapidity divergences. So it's because the abelian nature of the theory makes it kind of simple. So you still have to, there are other things you need to worry about. So for instance, you need to worry about all the logs, because you have to worry about the structure function of the electron and the structure function of the photon. Those are all there, but the difference, and those are there in QCD as well, but not these problems.
So you don't get any large rapidity logs like QED?
So I'm not sure if I have a proof of that, but I think so, yes.
Okay, thanks.
Okay, so so gravity is an effective field theory. Okay, so as you probably all know, the statement that gravity and quantum mechanics don't jive is a misinterpretation. It's a perfectly well-behaved quantum field theory as an effective field theory as long as all the invariant masses are much larger than the Planck scale. Okay, so you can write it down as a series. of higher dimensional operators, everything's perfectly well behaved as long as ST and U are much less than in Planck scale. But what happens in the Regge limit? So in the Regge limit, if we allow ourselves to have invariant masses much larger than the Planck scale, we know we should still get a sensible result, right? Because we know that planets scatter and that their S is much larger than M Planck, to say the least, okay? So it has to be some way to make a sense of this as an effective field theory, despite the fact that it seems to violate the usual rules of low energy effective theories. Okay, so how do we get around this problem? So we need to find some objects which are not sensitive, or some observables which are not sensitive to the UV completion, right? Unless we know the UV completion, we have to find something which isn't sensitive to the UV completion. And one way to do that is just to look at, we restrict ourselves to scattering at large impact parameters. So again, there's no large momentum exchange. The momentum exchange will be tiny. So we're going to eliminate the need to calculate diagrams like this, right, where we have S-channel, S-wave annihilation, which would have some modes in here which are outside the regime where the field theory makes any sense. But we can certainly consider forward scattering, and this should be an allowed process as long as there's no large virtuality loops in there, and that's great. The problem is, of course, gravity presents different challenges. Is that how do we power count in this theory? So we have a dimensional coupling. QCD was nice and simple because we only had alpha S. But because this theory is not conformal, we have more possible ratios. So we can form two-dimensionless ratio expansion parameters. Alpha Q, sorry if I go back between M Planck and G Newton. So GT is less than 1, controls the size of quantum corrections, and G squared ST controls the size of classical corrections. And if you were to put the H bars back in, you would see this guy has an H bar and this guy doesn't. So when this object, you can ask why can't I make this object as large as I want? And the answer is because this basically is controlling black hole formation. So when this object gets large, the Schwarzschild radius encompasses the system, and the system will collapse into a black hole. And so it shouldn't be a surprise that things are going to spiral out of control calculationally once that guy starts to become large. Okay, now that all seems well and good, but every time we exchange a Glauber, we actually get a factor of S over M Planck squared, which is huge. So it seems like Glaubers are going to completely destroy any hope of power counting, because we would give you an alpha C over alpha Q, which tells us we could put in as many alpha Qs as we wanted and still get something which is order 1, which is true. But we know that can't be right. Something has to happen to reorganize. There has to be more structure, because otherwise, as I say, we couldn't do planetary scattering. So there has to be some way the theory knows to reorganize itself. And we know it because what happens, it iconalizes. So if you go to impact parameter space, then what happens is that all the classical pieces exponentiate. And now we have a well-defined exponent here with a convergent expansion as long as alpha C is small. If you expanded it out, of course, you would see that there's interference between quantum and classical. But as long as you know as long as you can keep this form, then you can calculate, say, any classical observable you want by using Hamilton-Jacobi theory. You can differentiate this with respect to B and get scattering angles, and you can calculate energy losses and so forth and so on, all from knowing this exponent. So the exponent's well behaved, but it's predicated on the fact that this is iconalizing. This is iconiform works. And that's an interesting question. In the massive case, for massive particles, it's been proven. It's not too hard to prove that. But in the massless case, there's open questions, which maybe I'll touch upon. Maybe I'll probably talk about tomorrow if people are interested in coming to the seminar.
Sorry, I just have curiosity.
Yeah.
And so you were mentioning the DFK case, that one of the challenges there is you have a convolution in momentum space. So I assume going to impact parameter diagonalizes that convolution also in the QCD case, but maybe it doesn't help a lot because then you have 3 particle channels, and then for that maybe it's not.
Are you saying about solving the BF-Kell equation in impact parameter space?
Yeah, I mean going to impact parameter space maybe simplifies a bit some of the contributions, but maybe not all of them. That's the issue.
So the resummation that goes on in BF-Kell is dominantly quantum mechanical. So I don't expect it to have the same simplifications in going to impact parameter space than the usual resummations. Okay. So we can use our this effective field theory to look at what the expansion looks like. So basically, every time we add a Glauber, that gives us an enhancement, right? And if you have enough Glaubers, it looks like it's super enhanced, and we call those super classical. But those are just coming from the expansion of the exponent, right? So that's not terribly interesting. So every time we add a Glauber, we pick up a factor of alpha C over alpha Q. So these guys are what we call superclassical. And every time we add a collinear or a soft correction, that gives us an alpha Q. So if we're interested in purely classical corrections, not superclassical corrections, which are sort of trivial because they're iterations, then we're interested in this line. So we add a Glauber, and every time we add a Glauber, we have to add one softer collinear correction. And I'm talking about now in the massless case. In the massive case, it populates in between these odd. So these are all the classical terms. So PM expansion is an expansion in G. So this is called 1 PM. This would be 2 PM. But when I add another line, say by going across, which I have to do to go this way in this plot, then that's 3 PM, 5, 7, so on. We can also learn something about the logarithms that occur. So starting each time we add a quantum loop, that increases the number of logarithms by 1. So if we're interested in classical logarithms, then there's going to be one classical logarithm at 3 PM. There's going to be starting at log squared at 5 and 7 and 9 and so forth and so on. And that tells us something about the structure of the logarithms in the amplitude. Okay, now if we wanted to, we could resum these logs. So for instance, if we wanted to resum all the logs in this direction, that would correspond to the graviton-Regge trajectory. So all we have to do is calculate the anomalous dimension of the one Glauber exchange through this diagram. It has a 1 over eta pole telling you it's a rapidity divergence, and extract the anomalous dimension. So this gamma and this omega are related by a factor of 2. So this is the Regge slope of the Regge trajectory of the graviton. And this agrees with an older result by Lipitov. Now, I should say that there's no, summing these logs doesn't really, in some sense, isn't so well motivated, because even though you're summing these logs, at some point it becomes sensitive to the UV completion. In other words, our cube term could contribute a log here, which is something you've missed. So unless you have a UV completion, you're just summing a subset of logarithms in the theory. It would be interested, say, to choose, say, in string theory, to figure out how this resummation would be related to the string, including all the string modes. So we can also calculate the gravitational BF-Kell. And that comes from the anomalous dimension of the two Glauber exchange, and these are the diagrams that contribute. And here's the running of the soft function. Again, has a piece proportional to a delta function in the Regge trajectory. Those are coming from here. And you can sort of see why, because this is the Regge trajectory. And then there's this piece here, the H diagram, which gives you the Regge cut. These are called the Regge poles. This is called the Regge cut. And what's interesting is that this kernel is the square of the Yang-Mills kernel. And I think Lipitov could have his results, because Lipitov, there have been two calculations of this result, one by Lipitov and one by a group involving, I don't remember I know Chris White in another group, and I think Howard Schnitzer and Steve Nasulich. I apologize for anyone I leave out. And they seem to disagree on their results for reasons I never quite understood, but our result seems to agree with what Lipitov had, up to some UV pieces which he kept that we didn't see a reason to. So that this is kind of interesting. I don't think this had to have happened, and I think BCJ doesn't necessarily tell you that this has to happen, but it does. I don't think it's going to work beyond this order. And so finally, let me just tell you a practical result that we got using this methodology is we're interested in calculating the 5 p.m. log squared piece. And the way we got it, so this is where it would show up, which is a for loop calculation, which I don't know how to do. But there's no reason to do it because this is a leading log, so it should come from a one loop anomalous dimension, and indeed it does. So what you do is you calculate the anomalous dimension for gamma 3,3, which is just comes calculating. This is essentially just a one loop diagram because these Glauber loops are totally trivial. And then you just solve the RG equation. Now, we don't know how to solve it, but we can iterate it. So if we iterate it once, then we're going to pick up the log squared piece, and this is what the log squared piece looks like. And you can get the single log also, or the real part of the single log, by using dispersion relations and analyticity arguments. Okay, so I should mention there are some open puzzles. I think I did mention it, that ACV, and then pointed out when it comes to superplanking, scattering, especially in the massless case, there's questions about how much the power loss seems to be greater than the total amount of energy that goes into the system. There's questions about whether or not in the massless case it really iconalizes. And if it doesn't iconalize, then how do you make sense of that physically? Because it seems to be sensitive to the ultraviolet completion. And so these are things we're thinking about at the moment. So I should say, needless to say, the problem of forward scattering, both QCD and gravity, is still a mystery that we're slowly unraveling. I mean, it's been under study for a very long time, and it's not clear whether or not, as usual, when you start using different techniques for a problem, how much progress it will make. I mean, it's a very old problem and very hard one. I think in gravity there's still more room to grow because it hasn't been studied as well. So the QCD case has been studied for such a long time by experts in field theory. You can imagine that it's going to be harder to make progress in that area. And gravity has been studied it's only more recently been studied. So I think there's a lot of interesting questions to ask that are relevant both formally and to gravitational wave physics. Okay. So, thank you.
Thanks a lot, Ira, for this very nice colloquium. Questions? And I should use the cube.
So you have been discussing the case where you have this hierarchy between T and S, and how to resound the rapidity logs. And you have this example where we need to understand the planetary scattering, and there must exist an effective theory that accounts for that. You showed an example in this regime. Of course, planetary scattering exists also for large diffraction, and So do you have an idea how?
But it's still going to be a large impact parameter, right?
Yeah,
I mean,
still large input parameter, but T over S not necessarily very small.
So
Because the scattering angle could be, I don't know, 90 degrees. So is there a way forward in that different regime that you are aware of?
so there's sort of two different T's here, right? There's a T which is the typical momentum exchange of one graviton, and there's the T which is the physical impulse. And those are two different things, right?
Mm-hmm.
So the large scattering angle comes from differentiating the classical iconal to calculate what the scattering angle is going to be. But the logarithms that you calculate in the individual diagrams, that T is not that same T.
Yeah, it's much smaller.
Yeah.
So you would think you would be able to extend what you have been discussing
I would, yeah,
to larger.
I would think so. Yeah.
You know,
I would think
the
so.
physical T, say.
I would think so.
Okay, no, that would be very interesting. Okay, thanks.
Maybe let me ask a question about the log you were mentioning in the for loop.
Yeah.
So based on the analogy with two loops, so there in the amplitudes there are actually a lot of logs, but many of them cancel when you actually calculate an observable quantity, like going to the icon or going to PMOC.
Yeah,
so is that gonna?
So the leading log doesn't contribute to the to the radiation.
So how much below in the order of logs?
That's a good question.
Okay.
But the leading one doesn't.
Okay.
So yeah,
Yeah, so maybe could you go back to the UV sensitivity of the different contributions in the table, let's say in this table?
Here?
Yeah.
Yeah.
Yeah, you mentioned before that there are some computations which are UV sensitive. What are these?
Yeah, so these guys here, so what happens is that, if I start going here, I'm going to start to, I'm introducing more and more powers of T over M Planck. And at some point, say I could insert an operator, an R cubed operator into my diagram, right? And it'll contribute the same amount and scaling in the same way. So I can't trust my calculation. I can't, because there'll be stuff that I don't know.
So this happens in the green.
Yeah, anything in the green eventually will be sensitive to the UV completion.
Thanks.
Yeah.
So I actually have two questions. And the first, again here, if you look at a theory like n equals 8 supergravity, where you know that whatever ultraviolet divergences arise only arise at much higher loop order. So doesn't that mean that those worries are pushed up to higher orders?
Yeah. So if in n equals 8, so the question is this a useful calculation to do? And I would say only in n equals 8 maybe, or somewhere where you know that, or maybe there's no, I don't know. I mean, I know there's still.
No, first of all, there's also some number of loops to which the first ultraviolet divergence is pushed at lower in lower supersymmetric supergravity theories. But the question really is just that then there's some sense to at least the lower powers of alpha q times logs, right?
Yes.
Okay.
Yep. So yeah, if you start pushing up the counter terms to higher and higher dimension, then you'll gain more and more predictive power. So in that sense, for n equals 8, I think it might be interesting to look at these things. Yeah.
I mean, not for any practical purpose, right?
No.
The other question is really going back to the beginning of the talk. How do strongly coupled chiral gauge theories fit into your picture of what's understood and what's not understood.
Yeah, that's a good question because of the problem with chiral symmetry on the lattice. Oh, I'm assuming that, I haven't kept up on the latest, but I thought that they had made significant progress on that.
I don't think it's really a solved problem.
I see. Okay. Well, yeah, I guess that would be an exception.
I mean, in a sense, it's sort of, there's some analogies between that and having a chemical potential. Right?
Yes.
So,
But the question is that a conceptual problem or is that a technical problem?
I think it's more than just a technical problem, but that's
Okay.
just my opinion.
Yeah.
Okay, so I'm not sure whether this is a comment, a question, or just a stupidity, but going back from memories from decades ago, as far as I remember, well, you're discussing problems of large impact parameter scattering. The BFK equation is known to have issues at large impact parameter. Typically, it doesn't satisfy the Frossard bound that should be expected.
You mean the solutions to BFKL?
Right.
Yes.
There's a long tail at large
Yeah.
impact parameter
Yeah.
that doesn't integrate to the Frossard bound.
Yeah.
I'm wondering whether there's there's a trace of this here, and whether there's also something you're seeing there in the gravity side.
So, so the analog of that in the gravity side would be the onset of black hole formation, I believe.
Okay.
Whereas, so it's kind of, so the interesting thing about QCD versus gravity is the quantum versus the classical. So the classical in gravity is very easy to pick out. In QCD, it's not so simple. But the breakdown of the BFKL is the fact that you start, you can't cut off this thing in Glaubers, right? You've got an infinite number of Glaubers, and you're going to have soft radiation. The logs get huge when the impact parameter gets bigger, because T is getting smaller. And then the whole thing breaks down. And then there's something called the B-Jim-Walk equation, which I don't think there's any closed form solutions to it, but it seems to, and I'm far from an expert on it, but I think they claim that it starts to become unitary. I don't know. There may be experts in the audience.
But not solving the large impact parameter problem.
But isn't that
probably confirm, but then one could confirm as well. But I don't think it does, at least not on both sides. Maybe on one side, but not the other. Again, not.
Yeah,
I haven't looked into that for at least 10 years. So.
This is outside my knowledge base, so I don't think I can give you a good answer. I would have thought large impact parameter just meant that, the log's getting big, but maybe I
think there's more to it than that.
There's more to it than that. Okay.
Okay, thanks.
Yeah.
Any further question for Ira? Okay, then if not, let's thank Yami. And yeah, as you're also